Alright, it's section 2.1 today. We're talking about radical functions and transformations. So if you remember stuff from chapter 1, well, we're going to go back to that quite a bit. Transformations, remember that stuff? Yeah, shifting up and down. We'll get there in 1 second. But before we do that, I'd like you to take a look at maybe even section 1.4 from chapter 1. If you've got those notes with you, great. If you don't, not a problem. We'll do a quick review here. We talked about something called the inverse in section 1.4, and we had this interesting symbol f negative 1 of x, or the inverse of x. We also learned how to algebraically solve this. Now, if you don't remember the idea was to switch the x and y values, and then after that we had to go ahead and just solve for y, or isolate y. We also did it graphically, where we did a sketch of the graph and noticed that the inverse was really just a reflection in which line? Not the x-axis, not the y-axis, but in the line y equals to x, since we're switching x and y. So I think we did this example before, but let's just do it again. I want you to find the inverse of y equals x squared, both algebraically and also graphically. So we'll do the algebra first, and our first step, of course, is to switch x and y. So I'll have x equals to y squared. You're then asked to solve for y. Gotta get rid of that square by taking the square root on both sides. Be careful when you do that to put a plus minus in front, and therefore we have y equals to plus or minus root x. Or sometimes people will say the inverse, f negative 1 of x, equals to plus or minus root x. Okay? And how do we show this on the graph? Well, I guess I will graph out the original function first. That'll be the x comma y for y equals to x squared. Let's do negative 3, negative 2, negative 1, 0. I'm going to color code this, and you'll see why in a second. 1, 2, 3. Taking all the x values and squaring them. 9, 4, 1, 0, and then 1, 4, 9. I will ask you to sketch this out right now. Negative 3, comma 9, negative 2, comma 4, negative 1, comma 1. There's 0. Here's this side in blue. 1, comma 1. 2, comma 4, 3, comma 9. Here's my side in green. Notice it's symmetric. Beautiful. And if I were to ask you to now do the inverse, remember for the inverse we just switch the x and y. So 9 becomes negative 3, 4, negative 2, 1, negative 1, 0, 0. Let me switch colors once again. 1, 1, 4, 2, and then 9, 3. Let's graph these out now. So 9, negative 3, 4, negative 2, 1, negative 1. And I'm going to connect these dots here. Then we have 1, comma 1, 4, comma 2, 9, comma 3. And we get this. So notice the inverse is really kind of like a sideways parabola. And if you wanted to double check, remember that idea of reflection? Well, here's my line y equals x. Is it a reflection in this line? I think so. I hope you do too. So life is good. It makes sense. Now, remember in grade 10 when we had a definition of a function. A function was defined as a special type of relation where each element in the domain was associated with, that's right, exactly one and only one element in the range. So my question to you for this question, example number 1, is this inverse a function? Well, if I take a look at the value, let's say 4, I see that, hey, at 4, we've got the y value of 2 and negative 2, so obviously, nope, not in this case. So my next question to you is, well, okay, what restrictions would I need to put on the domain of y equals x squared so that its inverse is also a function? And this is where those colors come into play. Notice, if you go back to the graph up top, my sideways parabola is not a function. But if I just took the purple part, it would be. Or if I just took the red part, it would be. Because then, for every x value, there will be only one y value. Notice in my table of values over here too, that the blue values connect with the red. So if I wanted to keep the red, I'd have to look at the blue part of my original parabola. Similarly, the green matches up with the purple. So ultimately, if I want to just keep one of those parts, then on the original graph, I have to keep either the blue part or the yellow part. And that's what I want you to see here. What restrictions need to be put on the domain? If I kept the blue part, so there's really two choices, right? Two choices. The first choice here is if I were to keep the blue part, and that really means that I'm going to restrict the domain to now be between, or not between, just less than or equal to 0. Remember how we got these points? Well, what does that do? Well, what that does is, therefore, your inverse is just the bottom part of the sideways parabola. And that corresponds to the equation y equals to negative root x. So here's where I'm going to graph out those. Okay, f negative 1x. This is y equals to x squared. Right? Now, the other choice would be, or keep, was it the red part? I forgot what color I used. Oh boy. Oh, yes. Keep the green part. Green part. And of course, that belongs to this domain, where x is greater or equal to 0. And so I have this part of the parabola. And of course, therefore, the inverse is the top part. And of course, that just is this formula, y equals to root x. And there you have it, y equals to root x. So if I wanted you to put restrictions so that the inverse is also a function, you'd either have to use this restriction or this one. And notice it's always the boundary line being the axis of symmetry. Okay, now why is this important? Well, if you turn the page now, ultimately, this function y equals root x is really the basic square root function. Square root, or sometimes the more proper term is the radical function. And here are some quick characteristics of the y equals to root x, or the radical function. The left endpoint of this basic function is always 0, 0. As its right endpoint, well, there is none, because it goes on and on and on forever to infinity. How do we describe the shape of this graph? I'd say it's a sideways parabola. Sideways parabola. To be more specific, I'd say the top half of the sideways parabola. Its domain, well, if you look at it, it seems like it's every value of x that seems to be bigger or equal to 0. Yeah, you got that right. And the range, since we're taking the square root of a positive number, that also has to be, I guess, positive and I guess it could be 0, because you could take the square root of 0. So our range is just y is greater or equal to 0. A few quick table values. I'll use x as 0, so the square root is 0, 1, 1. Then I'll skip to 4, because the square root of 4 is 2. And then I'll skip to 9, because the square root of 9 is 3. Got it? Now, this chapter is all about then transformations, and oh, look at this stuff again. From chapter 1. So once again, I'm going to ask you now to compare the original function with this mixed up, messy one. We've got the a value, you've got the b value, you've got the h value, you've got the k value, and those are our parameters. They're the different variations and what they mean. So we're doing the exact same thing today. Chapter 1 all over again. So let's go ahead and try these out. I'll let you read the chart yourself, okay? So here's example number 1. I'd like you to sketch the graph of this radical function. Guess you should tell me what transformations occurred, and if you can see it, yes, that's right, 1 to the left, and that plus 3, if you guessed it, 3 up. Now, all you need to do now is just take every single one of these, what I call key points, which I've already given you, 0, 0, 1, 1, 4, 2, 9, 3, and shift them 1 left and 3 up. Do it. Done. Now notice what happens to your domain. Well, since this was a translation, your domain is also translated. 1 to the left means my domain used to be greater or equal to 0, but now I'm going to cross out the 0 and replace it with a negative 1. Same thing, the range used to be y is greater or equal to 0, but I'm going to cross that out and replace it with, you guessed it, 3 up, so 3. Let's erase to make it nicer. Okay, done. You try the next one. More transformations this time. I see. That 2 in front. Think back to chapter 1. Oh yes, reflection in the x-axis. Of course, that means you replace the y value with negative y in the coordinates. I see the 2, which is a vertical expansion by a factor of 2. And the x minus 1. How about some sort of horizontal translation? And that'd be 1 to the right. Okay, we're going to follow BERT, basic, then the expansion. So our first one will always be the expansions. Let's do that with all the points. Okay, so vertical expansion, 0 times 0 is, 0 times 2 is just still 0. Gonna expand this one here too, that'd be 1 comma 2. Expand, that'd be 4 comma 4. And then we'll expand this 9 comma 6. You can graph this out if you wish, but I'm just going to make this little chart and then I'm going to graph out the last one. The next thing, of course, is our reflection. So reflection changes the y value. 0 still stays the same. This becomes negative 2, negative 4, negative 6. Last but not least, the horizontal translation. So now let's shift everything 1 to the right. So 1 comma 0. Let's start graphing. 1 0. 2 negative 2. So 2 and then negative 2. There's, hopefully you can start seeing the doubling of the y values, the vertical expansion. 5, -4, and then 9. Oops, not 9. 10, sorry. -6. Whee! And there's your function. Y equals to -2 root x minus 1. Okay. Alright, last one's yours, the trickiest one. I'll give you a hint, as you might want to rewrite it in a nice format first, and then decide what you've got. Oops, I forgot. Domain and range. Ah, jump the gun, jump the gun, jump the gun. Well, the x value changed by going 1 to the right, so how about domain being greater or equal to 1? The y value is changed by the reflection, so it's no longer y greater than, but it's going to be less than or equal to. And I think it's just less than or equal to 0. Okay, now you try this one. Okay? Gave you a hint there. Rewrite it in this form first. Excuse me. By the way, you should be stopping the video. Don't wait for me. Try it on your own first. Those pesky negatives. That 2 is a horizontal compression. By 1/2. I see 2 negatives. Uh-oh. Reflection in the y-axis and x-axis. Yikes. And then I see a lot of shifting. 4. Is it 4 right? And then I think 3 down. Okay. Go for it. Key points. Remember? Key points. By the way, we better do the expansion compressions first. So the horizontal compression by 1/2. Then I think I'll do both my reflections. And last but not least, I'll do my translations. And then I'll graph the final one, find domain and range, then you're done. Just like chapter 1. By the way, reflecting 0, 0, no change. Since there's 2 reflections, I'm going to make both the x and the y negative. And now we're going 4 right. Okay, so 4 right, 3 down. 4 right, so that's like 3.5. 7/2. 3 down. 4 right, that's +2. 3 down. 4 right, that gives me -1/2. 3 down. I can pretty much tell the domain right now with the right and down stuff. X must be, oops, because of the reflections. Careful, reflections change the sign, right? So less than or equal to -4, and the range seems to be less than or equal to -3. Let's go and graph this out to prove it's true. Okay, our first point was what? 4, -3. And then 3.5, -4. 2, -5. And then -0.5, -6. Woo! Oh yeah, seems like my domain and range are correct. I hope yours is too. Alright. Alright, next example number 2. Then we got number 3, and we're done. Next one says, for each of these graphs, I want you to actually now write the radical form. You come up with the equation, okay? So let's take a look at these examples here. It says, for each graph, write the equation in the radical form of the form either y equals to a with the square root or y equals to root b. And really, I mean, I could use a or b, but one is usually conducive to the other. You actually have to decide, and I'll show you how you can do that. You do that by comparing it with the basic function. So always keep in mind the basic function. I'm just going to quickly draw that here, okay? 0, 0, remember? 1, 1. Then it was 4, then 2, and then 5, 6, 7, 8, 9, then 3, okay? Key points: 0, 0, 1, 1, 4, 2, 9, 3, okay? By comparing it with that basic one, then you can tell if it's a horizontal expansion compression or vertical expansion or compression. Okay, let's take a look at these two examples to help you out. You know the starting point is always 0, 0 on the basic. Where's the starting point on these graphs? Always, I guess, think about where the starting point is. So the starting point. How did 0, 0 get replaced? In this case, the starting point seems to be 2, 1. And it used to be 0, 0. Remember? It used to be 0, 0. So that's an indication, therefore, you've got some sort of translation. Right? 0, 0 became 2, 2. Can't be a reflection, can't be expansion. It has to be a translation. So in this case, probably 2 to the right and 1 up. Now that should be ding, ding, ding already for you because you've already found your h and k values. Okay, these help you find h and k values. All right, so now the question is it the vertical expansion, compression, horizontal expansion, compression, who knows? Well, if I were to start at this point, 0, 0, or sorry, not 0, 0, 2, 1. And if I were to kind of translate that basic graph there, it'd be what? 1, 1. So pretend this was 0, 0. Okay, pretend this is not my axis. 0, 0. Then I guess this is 1, 1. And this would be 2, 3, 4, 2, and so on. Well, obviously I think there's a reflection here. So if I had a reflection, probably in the x-axis, that would look like this. So, ding, ding, ding. We know there's already a reflection in the x-axis. Now, the final thing is this a vertical stretch or horizontal stretch? And the question is, how do you know? Well, I'm thinking here, look at the comparisons. You see how this height here is 1, where this one is now 3. Let's see if that's true for my next key point. This here is 2, and the whole thing is now how much? 1, 2, 3, 5, 6, 6. Looks like some vertical stretching has happened here, probably by a factor of, you guessed it, 3. So I think we've got a vertical expansion by a factor of 3. Putting all that together then, we have here y equals to a, which is 3. Oh, should I say actually -3? We don't have a b value in this one then. No horizontal stretch. Translation 2 to the right and 1 up. Done. Okay. It's the same idea for B, so let's see if you can go ahead and do it. Don't wait for me. Go. Looks like a reflection. Probably in the y-axis. So of course that means your B value is now negative. Alright. So if I were to reflect it negative, that'd be here. 1, and then 2, 3, 4 goes 2. I'm just drawing the basic one after the reflection right now, okay? 5, 6, 7, 8, 9, and then 3. Basic after reflection and translation to help me figure out if there's a vertical or horizontal expansion compression. Looking at the vertical, if I would look at that, this here's 1. This looks like a little bit more than 1. 1.5 perhaps. 2. Don't see 2.5, so I'm thinking, not vertical this time. Scratch that out. Erase. Erase. Erase, erase. So it's not anything vertical. Let's look at something maybe horizontal. So this unit was 1. Now it looks like my new graph is only half that. This distance here is 4. Looks like it's half that. 9. Yeah, half that. I think we've got a horizontal compression by a factor of half. So let's put it all together. What's our equation? Y equals to no A value in this case. Got a lovely B value, compression of a half, and you flip it around, B is equal to 2. Oops, got a reflection in the y-axis, put the negative in front. Then you've got your translations, 2 to the left, so x plus 2. And how about down 1, minus 1? If you got that, give yourself a pat on the back. Yay! Alright, one last example, and then we're done. I know, looks like pretty long, 6 pages, but not too bad. Okay, example number 3. Same as the Your Turn on page 71, so I just took this straight out from the book. So, company estimates its costs of production using this crazy function, C of n. So cost is dependent upon n, which is probably the number of items produced. 20 root n plus 1,000. It says describe the transformations represented by this function when compared to the basic function. Remember the basic function again is y equals root x. So if you look at here, I've got something with a 20. Well, that's a vertical expansion by a factor of 20. That's a lot. And then this plus 1,000 seems like a vertical translation, right? You're going up $1,000, I guess. Okay. Graph the function using graphing technology. Well, I can tell you right now, even without graphing technology, what it kind of looks like. Right? Here's the basic one. Oops, went up to 1,000, and then times it by 20, so probably more steeper like that. But if you wanted to check with your graphing calculator, please pull it out, and you can quickly graph it out. Once you turn it on, oops, that's interesting. AP Calculus, if you want to see what that is. Let's go to mode first of all. Let's change this back to function mode. Gonna quit here and go y equals 2. Let's put in our lovely function 20 root x plus 1,000. Probably want to change my window since it's 1,000. Oh yeah, not even close here. Don't know how far I want my x's. How about just 10 to see what's going on? How about to at least 2,000? Oops, too many. Graph! Ooh, nice and flat, I guess. Don't really see that sharpness. If I were to change my window, perhaps. Let's go up from 10. Let's change this to 2,000 as well. Let's just see what happens. Oh yeah, there you go. See? More of the increase. So what does the shape of the graph imply about the situation? Well, it looks like the more you produce, and of course that means your N, the higher the costs. But the costs seem to get less and less as you go forward. So it's not like you're increasing it at a faster rate. The higher is the cost, yes, but the rate at which the cost changes or cost increases seems to get less and less as you produce more. All right. Domain and range. Well, N is your domain. Looks like you gotta have at least 0 items. Range in this case is greater than 1,000, so your minimum cost seems to be $1,000, and it can only go up from there. This is not just your minimum cost. Sometimes in economics, this is what they call your fixed cost, because no matter how much you do, I guess if you produce 0 items, you still have to pay this company $1,000 as a setup fee, whatever it is, to actually start doing this production. Okay. Last but not least, use the graph to determine the expected cost to produce 12,000 items. Well, in this case, 12,000 items is what? Your C value or your N value? It's your N value. So using your graphing calculator to find this, I just ask you to press second calc, choose value, choose 12,000 items. Oops, do you know what I did wrong? My window, I bet you, is too small. Yes, see, 2,000, way too small. I want, how about 20,000 items? Woo! I'll just change my Y to match it up. Why not? Here's my graph. Second calc, choose 1, 12,000. So when you use this feature, you have to be in the actual window domain. So $3,190.89. Okay, you saw it there first. So from the graphing calculator, we got when x equals to 12,000, your y value equals to 3190.89. So that's your cost. I want to double check that with actual calculations. Go right ahead. I just ask you now to please plug in n equals to 12,000. So y equals to 20 root 12,000 plus 1,000. Once again, graphing calculator time. 20 root x Oops. I know what x is. 12,000. Add another 1,000. Let's see if we get the same answer. Oh, we definitely do. Life is good. And we're done. 3, 1, 9, 0, 8, 9.